Welcome to Math 119, where we are talking about Chapter 1.1, Real Numbers in Algebraic Expressions. So in this video, we are going to be talking about how to classify numbers, different types of notation, so interval, inequality, graph notation, some properties, and then some terminology at the end. All right, so we're going to start off with classifying numbers. And I'm sure you guys have seen some form of this diagram. So when we talk about classifying numbers, the reason why we're starting with this unit is that because sometimes on your homework, they're going to be telling you very specifically how they want you to orientate and structure your answers. So if they say, hey, you want to put it as an integer or a reduced fraction, you need to know, well, what the heck is an integer? Like what classifies as a reduced fraction, things like that. So when we talk about natural numbers, its notation is an n with 2 bars. So kind of like a double bar. Now, where do natural numbers start? What's the lowest natural number? Now, most students get natural and whole kind of mixed up. So natural, we're actually going to be starting at the number 1, and then we get to tick up all the way up to infinity. So natural numbers go from 1, 2, 3, and all the way up. So these are positive numbers that start at 1. Now in our diagram, natural numbers are the very middle circle. So this is like 1, 2, 3, and so forth. Now whole numbers is written as a W with 2 bars. Now, if you thought natural number was a certain number to start on, it's most likely that you're thinking of whole numbers. So what is the smallest whole number possible? Well, we start at 0 and we can tick up from there. Now, what do you notice in comparison with natural and whole numbers? Right? Well, natural numbers had the values from 1 and then up, which we can still see in whole numbers. So whole numbers, the only difference is that we start now at 0. So in our diagram, the very next circle will be your natural numbers, where you now start at 0 and then you slowly tick up and go forth, right? So natural numbers are found within whole numbers. Now, what is missing from our number line? Well, integers is going to be the very next one, which is what's missing. So integers is not I, it's actually going to be a Z with an additional bar, is going to be what's missing. So notice that in natural and whole, what's missing now are negative numbers. So going from negative infinity, and maybe I start at -2, -1, 0, 1, 2, and again to positive infinity. So now with the addition of negative. So now you have negative and positive numbers. Now, do you still have natural numbers included? Absolutely. Let me try that one again. We now have whole numbers included. And now we have some negative values. Come on, there we go. Now in your next diagram, right, we're just including your circle, making it a little bit bigger. So now we have negative infinity, -2, -1, and then still 0, 1, 2, 3, and so forth. Now, rational is what's next. So again, look at your number line. What is missing now? Well, we're missing the fractions, the decimals, things like that. So rational is not R. It's actually going to be a Q with a bar. Now, this is where your decimals come in. So we're still kind of sticking with that pattern that each one kind of gives a little bit extra. So we can still have negative values, and maybe we do a -1.5. Maybe we have a 0. Maybe we now have a 1/3, 1/2, right? A 1, 2. Let's tack something on. Let's see, 2.2222, right? And I'm going to tack on something else in a second. But rational numbers are values that now have some rules. Rules to rational. So one thing to look at are decimals. So with your decimals, right, thinking about some of these fractions that I just wrote out, right, like 1/3 and 1/2, right? Those values in its decimal form are 0.33333 repeating, or 0.50, right? These two are great examples of what it means to be irrational with decimals, because this first one is considered irrational when in the decimal form because it has a repeating pattern. So while it is continuous, it's continuous in some sort of a pattern. Or for example, this one, there's no pattern, but it does terminate. So it ends or terminates. So it is not continuous, it just full stops, right? So that's what it would mean with your decimal places. Now, if you see it here as well, 1.50, that is also a great representation, or even over here, the multiple repeating pattern, right? Now that's with decimals, but what about roots, whether they're square roots, nth roots, cubed roots? So for example, the square root of 4, what does that come out to be? Right? Well, that comes out to be 2, which 2 is classified as a natural, a whole, an integer, and now as a rational, right? A rational, not irrational. So any sort of root that comes out nice and clean. So whether that is in a cubed root, a square root, a fifth root, right? So any sort of root that comes out nice and clean, where the value is nice and presentable, this would be still considered rational. So I might tack on an extra one over here, perhaps the square root of 4, or the square root of 100. Whether that be positive or negative over here, we can maybe add negative square root 36, which is just another way to say -6. So this is where we can add in a few more extra values. So we have over here, we still have negative infinity, we got positive infinity, we got -1, 0, 1, 2, let's add square root of 4, let's add negative, I don't know, 4, no, 3 over 2, 0.5, right? Just things that might be present. Last up, we have irrational numbers. So irrational numbers is actually a Q star. So these are all numbers, right? Irrational numbers are opposite of rational. So opposite of rational. So that just means if rational numbers include all of these values here, actually, I'm going to get rid of that one, right? If all of these numbers here represent rational and integer and whole and natural, right? The opposite is to exclude all that. Exclude all of these nice looking values, and what do you end up with? Well, you end up with values that aren't nice looking, right? Decimals, right? Or unclean square roots. So let's say the square root of 2. Well, that's about 1.41. And then I kind of start remembering what comes after, right? I can only just generalize this number, right? Approximate, right? But the ... that comes after signifies that this value continues, but it continues without pattern. So when we talk about the decimal rule, it's going to be continuous without pattern or repeats, right? So the square root of 2 could be 1. Can you think of any other one where maybe it's a little famous that we kind of know of the first few values? Well, another one would be pi. Pi is irrational. It's approximately 3.14. Now, some of us might be able to recite a few more after that, right? Depending on the teachers you've had in the past. But there's an ending point. You can't just keep memorizing on and on and on because it just is continuous, right? ... We got another one, E, right? Which we're going to discover what E is later on in chapter 6 with our textbook, at least. So E, we're going to wait to discover what that value actually is. So irrational, you'll notice it has its own bubble. So values like pi, E, square root of 2, right? Just unusual values. I'm going to replace some of these. I want them to actually kind of stick out a little bit more. What was it? Kind of forgot. 1, 2, 1, 2, 1, 2. 1/3. I guess that one has to be negative. 1/2. Right? So things kind of like that. Okay. Now the last thing is real numbers. This is where we get to do R, not sorry, just R with a bar. So real numbers. The expression, I'm sure you have heard, all real numbers, represents all of these numbers that we have accounted for. So all of them from negative infinity to infinity. So all real numbers from negative infinity to infinity. So that being said, let's figure out on a number line, where do some of these values fall? So pause the video, see if you can figure out where these values fall on smallest to largest on the number line. Okay, so first up, we want to get the most negative value. So in our case, it is going to be this -15. So we can kind of cross that one off. And as we go down through the negatives, we have -3/4 and then -1/4. So we want more -3/4. And maybe we get kind of close to it, -1/4. And then we have 0, kind of over here. We'll say 0, we'll put right here. Scoot this over a little bit. So then we have 4, 3.14, which if we're just looking at those values, right, 4 can be over here. 3.14 is definitely less than 4. So we can cross those off. Then we're looking at the square root of 4 and the square root of 2. Well, the square root of 4, we know to be 2, so we can put that somewhere on the number line here, perhaps. And the square root of 2, whether we recognize we just did one with the square root of 2. But if you just think about it logically, if we have a bigger number underneath that has a 4, and you have this value under here of a 2, it's going to be definitely less than this 2 value. So it's going to be somewhere over here, the square root of 2, which is approximately 1.41. Continue this. Now that just leaves pi. So pi, right? What was pi? Well, pi is 3.14 dot, dot, dot. So that dot, dot, dot tells us there are values after this 4, whereas the other one just kind of stops. It's it. So we're going to put pi right directly after the 3.14. Now that being said, this is our number line. Can we then classify these numbers from above? Keep in mind what we know about the square root of 4 in case we get hung up on that. Okay, so looking at these values, natural numbers. So of these values, what is considered a natural number? So we have, let's see, we got 2 here, we got 4 here as being natural. So we have 4. We have the square root of 4, which is equal to 2. So that comes out nice and clean. Now, whole numbers, right? What is considered a whole number, right? What value have we added? Well, whole numbers still classify as having these clean values, right? And then a little extra. So now we get to add in that 0. With your integer, right? We're still kind of tacking on these values. I'm just going to keep writing, just wrote it 2. So we've had our values, and now what extra values can we give? Well, we can put 15 or negative 15 on here for sure, and that's about it. Okay, now what? We have rational, right? These are going to be your fractions. So other than the few that we can list, we have your fractions, negative 3/4, and we have negative 1/4. And I believe that is it. And looking at your irrational numbers, oh, I'm so sorry, I missed one. 3.14, that would still be considered your rational. And then the remaining square root 2 and pi would be considered irrational. Now let's talk about notations. So here we have interval inequality and graph notation. Now we have 2 ideas. We're either going to include or exclude these values. So wherever these values are at the end, we can determine whether or not we want to include, so we want that value, or exclude as we want to get very, very close to this value but not achieve it. Now in interval notation, to include a value is to use any sort of brackets. And to exclude is not a bracket, but exclude is to use parentheses. And all this is saying is we start at the value, or we start close to the value. Now, to represent the same idea but in inequality notation, this is when we get to say we have greater than or equal to, or less than or equal to. And notice that we're saying equals to at the very end of those statements. That is what it means to, again, include. We're starting at the value. Let me copy and paste that. Copy, paste. We're starting at the value. Whereas if we're exclude, we're getting close to the value. We can just say greater than or less than. Now, if you have a hard time remembering which one is greater than or less than, some of us, I'm sure, remember like an alligator's mouth, which is like bigger and smaller. If you can't remember that, an easier thing is that the less than sign looks like it spells the letter or the word less, whereas the greater than, I guess I'll capitalize it, G are, it looks like the greater than from greater than sign. Okay. So just kind of a tidbit, greater than, less than, kind of helpful, maybe not helpful. Just like to provide something, right? And again, these values are telling us that we're starting close to that value, not on it. And last but not least is graph notation. So to include, we're going to see a closed circle. Nice and closed. You could also see it as any sort of bracket. Again, we're starting at the value. And if we want to exclude, it's going to be open, kind of like breezing right through that value. Or we get to use parentheses. You can use also both. It doesn't matter one way or the other. Now, one thing to note before we get started, can you ever include affinity? Can you start at infinity, or can you start really close to infinity? Right? Well, to include means we can start, we hold that value, we are achieving that value. But infinity, right? We can't reach infinity. We can't hold it, we can't grasp it. We're just kind of running towards it at the end of the hallway, right? It just keeps getting longer and longer. So with that in mind, when we're talking about infinity, we will never include infinity. So we'll always have some sort of a parentheses around an infinity sign. So if that's all you kind of need to get yourself started, definitely try out the remaining on this page. We can kind of mix and match with the interval inequality notation as far as including and excluding, but just give these a shot on pause when you need to. Okay. So first off, if this is the first time we're seeing this perhaps in a while, right? How can you go about reading something like this? Well, this is x is greater than 0. X is, and I won't write all of them, greater than 0. And because there's no bar underneath, we don't have to say equals to. So if x is greater than 0, if I were to make a number line, 0 being my key feature, well, where are the values greater than 0? Well, to the right are values that are bigger than 0, right? Greater than 0. So we want to be going towards those values. So we want to go as close as we can to 0 and then go up. So are we going to have a closed circle or an open circle or a bracket or a parentheses? We said based on your notes above, if we're not going to be able to start at that value, right? We said just greater than. We're talking about having some sort of open circle or a parentheses. So open circle or parentheses. And again, trying to go that way. So then if we put it into interval notation, I'm a huge fan of using bracket or parentheses, right? We read left to right. So the smaller number first, ours is 0. We go towards our largest number being infinity, right? Left to right, left smallest, all the way to right, which is our biggest value. Now we get to figure out, okay, do we have parentheses or a bracket? Well, we just had we just talked about this open circle also being represented as a parentheses. So we're going to be using a parentheses around your 0, right? We said, hey, this is where we exclude your value on the interval notation. We're also going to do the same around your infinity, because as we said, we are never including positive or negative infinity. It's not achievable. So that would be your first one. Let's try it again over here. So again, how do we say this? Well, x is less than negative 1/2, right? It does not have that bar underneath, so it's not going to be an equals to, so it's just less than. So again, I like to start with a graph. We have our key value of negative 1/2. So where are the values less than 1/2? Well, you have these values. Let's say this is -1, -2, -3, and so forth towards negative infinity, right? We're going to be going this way. Now, do we include or exclude this negative 1/2? Well, again, we did not say less than or equals to, right? There's no equals to, so we are going to be using an open circle or a parentheses. So then when we do your interval notation, right, your smallest value at the very left-hand side, right, is what value? Well, the smallest value on the left-hand side is negative infinity. And we go all the way up to your right-hand side, and what's your largest value? Well, your largest value is that negative 1/2. Now, we just have to determine, are we including or excluding these values? Do we ever include an infinity? No. So parentheses around here. And as we said last time, if we have your graph notation, if we're using your parentheses or bracket notation with your graph, it's just an extension of that. Now for this one, we have it in interval notation, and we need to write it in inequality notation. So this is kind of the reverse of what we have been doing. So now, how would we read this one? Still left to right, and we're going to kind of break it up. We're going to say x is greater than your first value, greater than negative infinity. And notice that we're not saying equals to, because this is a parentheses, not a bracket. So we're greater than negative infinity, and x is less than -9. So more negative, right? We're less than. So on a graph, we have your -9 as your key value, and values that are less than -9, -10, -11, right? All the way down to negative infinity. So now, are we going to be including or excluding this -9? Excluding, a parentheses, a circle, and we're going towards that negative infinity. So again, to write it in your inequality, you need your left, your right most values. So negative infinity, -9. We're going to be assuming that we're talking about x on your domain. If we talk about your range, we're going to swap this x for a y. We're just going to be using this notation. When you read it back, again, just think about x is greater than negative infinity. And then x is less than -9. So it's all about kind of reading it one way. And one more time. X is greater than negative infinity, and x is less than positive infinity. So on your graph, oops, one more time with that graph. We have negative infinity out here. We have positive infinity. Those are our key features, and we are going between those values. So again, in your inequality notation, we're going to be putting your two values, your x in the middle, and because we're just talking about not being equals to, we're just x is greater than your negative infinity and less than your positive infinity. Let's try this one. So we have -3, or I should say, well, again, we'll break it up. X is blank, -3, x is blank, 5. Well, x is greater than and equals to -3, and x is less than 5. We know it to be greater than or equals to because of this bar right here, whereas it's just less than because there's no bar. So if we were to graph it, we're going to have the same number line, -3, we got 5. Those are our key values. We're going to be bouncing in between these values here. And then let's take a look at this -3, right? Because we're saying x is greater than or equals to, right? Are we now going to be a parentheses or a bracket? Well, we're going to be a bracket or a closed circle. We're starting at -3 as opposed to, okay, we can try and get as close as we can to 0. So 0.01 or 0.0001 or 0.000001, right? Trying to get as close as we can to that 0 versus, hey, we are starting at -3. Doing the same, we can go all the way up to 5 with a parentheses or an open circle. Then for your interval notation, writing those values again. And, oh, so sorry. I'm in the wrong notation. -3, 5. And because we already have it written on your graph as its notation, we can just transfer with the bracket and parentheses. Let's try it again here. X is blank, oops, then 0.20, and x is blank. Okay, so x is less than, nope, greater than, but less than or equals to 4. So again, in that graph notation, we have 0.20, we have 4, we have closed circle, bracket, open circle, parentheses, and we are hovering between those two values. Okay, we're coming up on the last ones. Again, just watch the video or watch as much as you need to for this part, because I know for the majority of us in 119, we've experienced this lecture before in high school or perhaps in a different semester. All right, so let's take a look at this graph and the inequality. I'm just going to go right for the graph notation. We are having brackets, so we can include those two brackets or a closed circle hovering between these two values. And for its inequality, we have 1/7, x, and 10. And because we are working with brackets, we're just going to be saying less than or equal to on both. So it should have that bar. And the last one, we have your graph notation. We have -8. We are going above -8, so x is greater than or equal to -8, meaning we have closed circle bracket. We're going towards positive infinity, which means we got your notation here. Now there's two ways to write it in this form with your inequality, because one is redundant. The one I'm writing here is redundant. It just says x is less than or equal to greater than or equal to -8 and less than infinity. Now we can take a part of that. We're just going to be erasing this part here, which is less redundant to say because we're just saying x is greater than or equal to -8. So any value beyond -8 to the right, we are going to be greater than those values. Whereas if we're saying x is greater than or equal to -8, but less than infinity, it's just, again, just making that statement over. All right, now we got some algebraic expressions and field properties. So let's take a look at the following situations. Now we're going to be doing a lot of evaluating in our class. So we start with just evaluating when it comes to a certain value we put in for a variable. So in our case, evaluate this expression, 5x to the third minus 16 is equal to, or sorry, for when x is equal to 4. That is just saying, okay, replace your replace your x value here with a 4. So you'll be seeing me a lot put in some like blank spaces. That is so that I can fill in a 4 for these values, right? I leave space for whatever we're filling in. Then it goes from orders of operations. So orders of operations, think about PEMDAS, right? Parentheses first, so any sort of grouping, so parentheses, square roots, absolute value signs. We want to take care of all of the inside stuff first. Then we can take a look at your exponent, which is what we're going to be doing. And then multiplication and division, it just happens in the order of from left to right. So whatever happens first, and then we always add and subtract at the very end. All right, so let's take a look. 4 cubed, we have 64. Now, if you don't know what to do with 4 cubed, we can just say is just 4 written out 3 different times. So 4 times 4 is 16 times another 4 is 64. So 64 times 5 minus 16. We then get to do your multiplication, and there is nothing wrong with the old school multiplication. So we have 20, we have 30, 32. So you got 320 minus 16. Again, old school subtraction if you need it, 304. Try it again for your next one. So pause the video, see what you can come up with. Now this time we have x is equal to -2. So all of these x values here, we're going to sub in a -2, making sure you use parentheses. And then we're going to sub in a 3 for y. So you have -3. I'm going to leave a gap, -2 plus that. Let's see, we enter in a 3, a -2, and another -2. Okay. Now we get to evaluate. Keep in mind, if we're still having a hard time with your exponents, and maybe even trickier with a negative value, this is just saying we have 2 -2s written out, or one with parentheses. So we have really a +4 coming out. -2, again, any sort of grouping we want to take care of. So -2 plus 3 gives us a +1. Then we can go ahead and do multiplication. 2 times 1 is just 2. And then go ahead and subtract. Okay. So just very slowly introducing, evaluating. We're going to get to higher degree of difficulty later on in this semester, just to get us warmed up for our calculus classes coming up. Now you have some field properties. You have commutative, associative, distributive, and you have both the additive and the multiplicative. Really, it's just saying for your commutative property, you can reverse the order when you add or when you multiply, and it's still going to come out with the same response. Associative just tells us that, hey, you can group it in any different way. whether it be multiplication or addition. And again, it's still going to come out the same way. Distributive for your multiplication. If it's grouped out here, we can just go ahead and distribute your A value in to each term, no matter how many terms are in there, but it's got to be to each term, and then it'll come out in the same manner as if you were to add and then multiply. Now, a little bit more with your, what are these called? Orders of operations. See what you can come up with for A and B. Pause the video as you need. Okay, so first off, with your orders of operation, again, taking a look at your groupings. So you have brackets. You also have parentheses in the middle. You do have a double negative, which we then turn into positive. Double negative, this can be really written as -1 times -1 times a +8. So those positive or negative ones cancel and come up with a +8. So we now have 2 + 8. So 3 times 10, which is equal to 30. Trying it again here, a little bit bigger. Again, before we take a look at any sort of addition or multiplication happening in your grouping, we definitely want to take a look at your exponent first. We have 4 plus 3 to the 4. So again, keep chipping away at it. We have to multiply before we can get to adding. We have, let's see, 16. And then 1/2 of 16 can also be written as 16 divided by 2, right? If we're thinking about these as being a fraction, we can just multiply your top to top and your bottom to bottom. So 16 divided by 2 is 8. And the last thing we're going to cover is terminology of algebraic expressions. So it says, consider the following, or sorry, consider the algebraic expression. So we have this whole thing right here. So how many terms are there? Well, first we have to figure out, well, what the heck is a term? Now, terms can be identified as combinations, or terms are combinations of addition and subtraction. So you can identify them with a series of addition and subtraction between values. What I mean between values is, notice that in here, yes, this value here has an addition sign between it, but the bigger picture is that you have something here, let's call this A, and something bigger here is being multiplied to it, right? We don't really care that x squared plus y squared are, x squared plus 4y are happening, right? We don't care about that addition, because the real big picture in this first term is that you're multiplying these two ideas together. And then again, you're multiplying this 5 with your square root of x. And then you have this 13 that's hanging out, right? So really, how many terms are there? Well, there's 3 terms. You have the -17x, x squared plus 4y, that's 1 term. You have 5 square root of x, that's another, and this -13. Now, what are the factors within your term, right? Factors, think about factors are just a series of multiplication. So think about factors, or even think about a factor tree, right? What multiplies up to 12, right? 1 and 12, 2 and 6. Not 2 and 4, 3 and 4, right? Factors of 4, 2 and 2, right? We can get all of these values here as your factors. So if we look at it in the same sense of terms, right? If we're talking about series of multiplication, we could have written this 12 as having 3 times 2 times 2, right? 3 times 2 times 2, right? A series of multiplication. Where would you put your multiplication values, right? Your multiplication symbol. You'd put one right in between -17 and the x. Those values are being multiplied. You're also multiplying your x by this parentheses. And while I understand the temptation to put another multiplication between 4 and y, yes, you are totally right. There is multiplication between those. But when it comes to factors of the term, we said, hey, this is your term, right? It's really this parentheses that matters. Anything on the inside doesn't matter so much. So really your factors are -17, x, and that parentheses. So you have 3 factors here that make up this one term. Now, last one we're going to talk about is coefficients. What are the coefficients of all of your terms from above? Now, if you don't know what a coefficient is, a coefficient is the, oh, come on, numerical value of the term. So the number in front of each term, typically attached to the variable. So what are your coefficients of your term? Well, your coefficients from the very, very big one above. The numerical value is -17 and 5. Again, we don't really care so much about this 4 and this x squared because your term, this is one term, the identifying term has the numerical value of -17. The numerical value of this term is 5. There's 5 of these square root x's. And your last one, -13, has a special name, is a constant. No matter what your variables are doing, this value here, this -13 term, is going to just remain smooth throughout. It's never going to change because it's not attached to a variable. When it is attached to a variable, no matter what number we put in, those variables are going to change. But the number itself, if we just added something like this, -16 would be the constant, right? It's not going to change. We're always going to subtract this -16. So that's the difference between a constant and your coefficient. And that wraps up chapter 1.1.